Welcome to our comprehensive video on the standard model of particle physics and its Lagrangian formulation. In this video, we'll explore the mathematical framework that describes the fundamental particles and forces in our universe. The standard model is our most advanced and well-tested theory of particle physics, describing three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Let's begin by looking at the particle content of the standard model. The standard model includes two main categories of particles: fermions, which are the matter particles with half-integer spin, and bosons, which are the force-carrying particles with integer spin. Fermions include 6 types of quarks: up, down, charm, strange, top, and bottom. These quarks come in 3 different colors, which is a property related to the strong nuclear force. Fermions also include 6 types of leptons: the electron, muon, and tau, along with their corresponding neutrinos. The gauge bosons include the photon, which mediates the electromagnetic force, the W and Z bosons, which mediate the weak nuclear force, and the gluons, which mediate the strong nuclear force. Finally, we have the Higgs boson, which gives mass to other particles through the Higgs mechanism. Now, let's dive into the mathematical description of the standard model, the Lagrangian formulation. The Lagrangian is a function that contains all the information about the dynamics of a physical system. For the standard model, the Lagrangian describes how particles move and interact with each other. The full standard model Lagrangian is quite complex, but we can break it down into several key components. L equals L of gauge plus L of fermions plus L of Higgs plus L of Yukawa, where L of gauge describes the gauge boson kinetic terms and self-interactions. L of fermions describes the fermion kinetic terms. L of Higgs describes the Higgs field and its potential. L of Yukawa describes how fermions interact with the Higgs field. Let's explore each term in detail. Let's start with the gauge sector of the Lagrangian. The gauge sector describes the kinetic terms and self-interactions of the gauge bosons, which correspond to the fundamental forces: electromagnetic, weak, and strong. The gauge Lagrangian is given by L of gauge equals negative 1/4 F superscript a subscript mu nu F superscript a subscript mu nu, where F superscript a subscript mu nu is the field strength tensor for each gauge field. This tensor is defined as F superscript a subscript mu nu equals partial derivative mu a superscript a subscript nu minus partial derivative nu a superscript a subscript mu plus G F superscript ABC a superscript B subscript mu a superscript C subscript nu, where the first 2 terms represent the kinetic energy of the gauge fields. The last term represents self-interactions between gauge bosons, which exist for non-abelian gauge theories like the weak and strong forces. The gauge symmetry of the standard model is described by the product of 3 groups: U1 for electromagnetism, photons; SU2 for the weak force, W and Z bosons; SU3 for the strong force, gluons. Under gauge transformations, the gauge fields transform in specific ways to ensure that the physics remains invariant. Next, let's look at the fermion sector of the Lagrangian, which describes the kinetic terms for quarks and leptons. The fermion Lagrangian describes how fermions propagate through spacetime. The fermion Lagrangian is given by L of fermion equals I bar psi gamma superscript mu d subscript mu psi, where psi represents the fermion fields, quarks, and leptons. Bar psi is the Dirac adjoint of psi, gamma superscript mu are the Dirac gamma matrices. D subscript mu is the covariant derivative, which includes the gauge interactions. The covariant derivative is defined as D subscript mu equals partial derivative subscript mu plus I G a superscript a subscript mu T superscript a, where G is the coupling constant for the respective gauge interaction. A superscript a subscript mu are the gauge fields. T superscript are the generators of the gauge group in the appropriate representation. This structure ensures that fermions interact with the gauge bosons in a way that preserves gauge invariance. The left-handed and right-handed fermions transform differently under SU2, which is crucial for the weak interaction. Now, let's discuss the Higgs sector of the Lagrangian, which is responsible for the generation of particle masses. The Higgs sector describes the dynamics of the Higgs field, which acquires a non-zero vacuum expectation value, VV, through spontaneous symmetry breaking. The Higgs Lagrangian is given by L of Higgs equals D superscript mu phi, dagger, D subscript mu phi, minus V of phi, where phi is the Higgs field, a complex SU2, doublet D subscript mu is the covariant derivative. V of phi is the Higgs potential. The Higgs potential has the famous Mexican hat shape and is given by V of phi equals negative mu squared phi dagger phi plus lambda. Phi dagger phi squared, where Mu squared is a parameter with dimensions of mass squared. Lambda is a dimensionless coupling constant for mu squared and lambda both positive. This potential has a minimum not at phi equals 0, but at phi dagger phi equals mu squared over 2 lambda equals v squared over 2. This non-zero vacuum expectation value triggers spontaneous symmetry breaking, leading to the Higgs mechanism, which gives mass to the W and Z bosons while keeping the photon massless.